Today we are going to study Lagrange method to optimize a function and bordered Hessian determinant. And let us consider this function, that is maximize u of xy equal to 2xy. Here x and y are complementary goods. Why? Because if we put the value of x 0, that is if we are not consuming or this particular consumer is not consuming the x and y only, what happens, the utility will become 0 and vice versa. That is if we are consuming only y or x, the total utility function will give you 0 utils. And subject to the constraints are 3x plus 4y equal to 90. That is p1x plus p2y equal to m. Two constraints are there. So first we have to, in order to derive Lagrange method, we have to convert this function is an equality to 0 format. That is 90 minus 3x minus 4y equal to 0. That is we have transferred this 90 to left hand side of the equation. So 90 minus 3x minus 4y equal to 0. Again m minus p1x minus p2y equal to 0. Then we have to add lambda. Lambda into 90 minus 3x minus 4y equal to 0. And then we have to add this main function, utility function 2xy here in order to get the Lagrange function. That is 2xy plus lambda into 90 minus 3x minus 4y. Now we are moving on to the first order condition. First order condition in order to get the bordered Hessian. That is dou L, that is dou partially derivating this Lagrange function with x, with respect to x. That is dou L by dou x equal to 2y minus 3 lambda is equal to 0. So how we get this 3 lambda? This lambda has been multiplied with this function, that is 90 lambda minus 3 lambda x minus 4 lambda y. Then we are differentiating this function with respect to x. So we will get 2y minus 3 lambda equal to 0. Again dou L by dou y, we will get 2x minus 4 lambda equal to 0. Then we are partially differentiating this function with respect to lambda. So dou L by dou lambda is equal to 90 minus 3x minus 4y equal to 0. Why? Because this is a constant here and lambda is to be differentiated with respect to lambda. So 90 lambda will give you 90 minus 3x lambda will give you 3x itself and minus 4y lambda by differentiating with respect to lambda will give you minus 4y, and we are putting it equal to 0. So these three equations we have to derive by differentiating, partially differentiating with respect to x, y and lambda. Now, yes, so we are now deriving the value of y and x. So this two equations 1 and 2, when we appropriate this two equations, that is 2y minus 3 lambda equal to 0, we will get 2y equal to 3 lambda. Then 2x minus 4 lambda equal to 0, when we appropriate, we will get 2x equal to 4 lambda. Now we can write it as 2y by 2x equal to 3 lambda by 4 lambda. So this lambda and lambda will get cut off, and 2 and 2 we can cut in that equation. So what we will get? Y by x equal to 3 by 4. Then y equal to 3 by 4x. Now you all know how to determine the other three unknowns of the equation. That is, when we substitute the y value in any one of the equation, we will get the x value. 90 minus 3x minus 4y equal to 0 is an equation. So in that equation we can substitute the value of y. So what will happen? 90 minus 3x minus 4 into 3 by 4 y equal to 0. So what happens? This 4 and this 4 will get cut off. So 90 minus 3x minus 90 minus 3x minus 4 into 3 by 4x. That is y equal to 3 by 4x. So we are substituting the y in place of y 3 by 4x. So what we will get? This 4 and 4 will get cut off. So 90 minus 3x equal to 0. So 90 minus 6x is equal to 0. So 90 equal to 6x. X equal to 15. Okay. Then this x value can be substituted in order to get the full value, exact value, numerical value of y. That is 90 minus 3 into 15. That is x. X value has been substituted here, minus 4y equal to 0. Then 90 minus 45 minus 4y equal to 0. So 45 minus 4y equal to 0 and 45 equal to 4y. So when we divide when we divide this 45 by 4, we will get 11.2. So y equal to 11.2. Now we can substitute this x value in one equation in order to get that is 2x minus 4 lambda equal to 0. In this equation we can substitute the value of x equal to 15. Then we will get the lambda value, numerical value of lambda, that is 2 into 15 minus 4 lambda equal to 0. 30 minus 4 lambda equal to 0. 30 equal to 4 lambda. Lambda equal to 30 by 4, that is 7.5. 7.5. And here we have to consider why we are executing or why we are including this lambda in order to get an optimized value in a function, because this lambda represents change in utility, change in main utility function. Not only in utility, whatever be the function, here it is utility. That's because I call it as utility. So the change in utility, when we change one of the constraint, here m represents the money, that is budget constraint. When we change the budget in one unit, what happens to this main utility is represented by lambda. So this lambda represents shadow price of an equation or a function. Okay. Now we move on to bordered Hessian determinant. So bordered Hessian, as the name itself indicates, it is bordered. That is, first we have to write to form a determinant. First we have to write the Lagrange method first order condition. Not first order, second differentiated value, that is Lxx. That is, we are differentiating second time the Lagrange function with respect to x, that is Lxx. Then we will write Lyy here, that is the leading diagonal is represented the extremes. Here we put 0 and the center value it is given as Lxx, and the leading diagonal third value is Lyy. And then we have to write Lxy, that is the Lagrange function to be first we have to differentiate with respect to y and then x. Here Lyx, that is first we have to differentiate x with respect to x and we have to differentiate that function with respect to y. In the second order we have to differentiate it with respect to y. And these four values are bordered by first order determinant of the main constraint. First order determinant of the constraint. So gx represents the differentiated value of this constraint with respect to x, and gy represents differentiated value of this constraint with respect to y. Again gx is first order differentiated value of this constraint with respect to x, and this is with respect to y. So the constrained first order differentiated value of the constraint is bordering the Lagrange function, second order Lagrange determinant, differentiated value. That is, this is second order determinant with respect to x, this is second order determinant with respect to y, and this is a second order determinant with respect to x, and this is second order determinant with respect to y. So here the values are this. First we will put it as 0, and gx, that is first order differentiated value of 3x plus 4y with respect to x. 3x with respect to x is 3. 4y is a constant, so it will become 0. So 3. Then the differentiated value with respect to y. So what happens? 3x is a constant, so it will become 0, plus 4y with respect to y is 4. Again here bordering, we are bordering gx, it is 3, gy, it is 4. Then Lxx means we have to differentiate this again with x. So all the values are constant, so we will get 0. Again this value, for this value we have to differentiate this 2x minus 4 lambda with respect to y. So what happens? All the values are constants, so we will finally get 0. Then here Lxy means we have to differentiate this dou L by dou y with respect to x. So what happens? It will get 2. The value is 2. Again Lyx means we have to differentiate this dou L by dou x with respect to y. So this will be constant, and 2y with respect to y is 2. So this is the determinant, bordered Hessian determinant. When you consider normally the value, you will get 48. The determinant value of this determinant is 48, which is a greater than 0 value, and this is the condition. So the values, these values surely will get optimized. Thank you.